Hello.
Hello, hello. How are you guys?
Good, how are you?
I'm doing good too. Are you guys feeling ready for Friday's midterm?
No.
No,
Yeah.
it's a lot. It's a lot of material. Have you guys attempted this practice midterm yet, or you guys haven't looked at it yet?
I went through it once today, but yeah.
Okay, okay. Were you able to understand the problems here, or were there any problems that you were stuck with?
Yeah, so. Um yeah. I'm okay, but I'm gonna kind of like listen a little bit more. So, like
Mm-hmm.
take it away.
Okay, so pretty much what I wanted to focus on the most was the predict the product section and the showing the mechanism
Okay.
questions.
Right. Okay. So questions 5 and 3. Okay. So for predict the product, let's start with 3A. We have this reactant molecule over here, which is a haloalkane. And then this is a stepwise predicted product problem where the first step is magnesium. What would magnesium, like ignore everything else, we're not going to be worried about that. If we put Mg, magnesium, to this haloalkane, what do you think is going to happen? Like where would the magnesium go to this molecule here?
To the bromine?
Yeah, so it's gonna go in between the bromine and carbon. So we're going to have this MgBr here, and there is a very specific name of this reagent, which is a Grignard reagent. Right? And what do you know about Grignard reagents? Are they nucleophiles or electrophiles?
Electrophiles?
So electrophiles are going to be positively charged, which will get attacked by nucleophiles, right? If you see this carbon here directly attached to the Mg, that carbon is going to be negatively charged like that, right? And this negatively charged carbon is going to be the nucleophile that's going to attack an electrophile, right? Something that make it more sense is this right here. Nucleophile is going to be nucleus loving, right? So they're gonna love nucleuses, which are consisted of protons and neutrons. So the overall net charge of a nucleus is positively charged. So if a nucleophile loves positive charge, they themselves are going to be negatively charged, right? Because opposite charges attract. Like negative charges are attracted to positive charges. So an electrophile is going to be electron loving. So they're going to love electrons, and the electrons are negatively charged. So if they love electrons, the electrophiles themselves are going to be positively charged because opposite charges attract. Right? Okay. So whenever you see MgBr here, the first atom attached to the Mg is negatively charged, making it the nucleophile. That's the end of the first step. We're done with the first step. Now we're bringing the second step, which is CO2, carbon dioxide. So I'm gonna draw out the CO2 out in this form over here, which is Lewis structure, right? And notice how this carbon here is attached to two electronegative atoms, oxygen here. Like, what partial charge would you expect this carbon to have if it is attached to two electronegative oxygen atoms?
Positive charge?
Partial positive charge, right? So we know that this carbon here is the electrophile because it's positively charged. We know this carbon here is the nucleophile because it's negatively charged. And the nucleophile will attack the electrophile, right? So this starred carbon here is going to attack this dot carbon, right? And that attack is going to make a new bond between the star and dot carbon. When we make a new bond right here, this carbon here is going to have 5 bonds, right? 1, 2, 3, 4, 5. That's not good. We don't want that because it breaks the octet rule. So to conserve the octet rule, we have to push the double bond onto the oxygen like that, right? Like push one of the bonds, which represents 2 electrons, onto the oxygen like that. the MGBR will dissolve away in the solution. So as a result, we're gonna get this as the intermediate. This is the starred carbon, this is the dot carbon, and this right here is the neo bond between the star carbon and dot carbon from that attack, right? And we see that this dot carbon here is attached to a carbon double bond oxygen and a single bond O minus. This single bond O minus comes from here, from this like if I highlight this oxygen over here in purple, that's that oxygen in purple right there. If I highlight this oxygen in pink, that's that pink oxygen right there, right? This dot carbon right here is this dot carbon. This star carbon here is that star carbon. And then this is the new bond between the star and dot carbon from the attack. MGBR goes away in the solution. Right? Any questions on how I got to this point here, Zenith? Oh, Zenith?
Yeah, that makes sense.
Okay. Okay, that's good. So now from here, we have a H plus workup, acid workup. So we're gonna use that to protonate the negatively charged oxygen to get to our neutral carboxylic acid like that. Right, so that's the final product here. And notice how before the reactant molecule had 1, 2, 3, 4, 5 carbons. In this molecule, we have 1, 2, 3, 4, 5, 6 carbons. So we have 1 extra carbon. This extra carbon right here came from the CO2 right here. That's the extra carbon right there. Right, okay. Okay. So I'm going to give you a similar problem here, and I want you to describe to me what the mechanism would look like, because I also show you the mechanism. But let's say now we have this reacting with that CO2 and H plus workup. What would happen in the first step?
The magnesium would go between the carbon and the bromine.
Mm-hmm. Correct.
And then the CO2 would attack the carbon.
So the CO2 here, what charge is this carbon here? Is it negatively charged or positively charged?
Positively charged.
Positively charged. So it cannot attack anything. It's going to get attacked, right? Because the things that will attack something are negatively charged. So what is the negative charge here that's going to attack this positive charge carbon here?
One of the double bonds.
So the double bond here is part of the carbon, right? So that's not gonna attack anything. It's gonna be somewhere in this molecule here. Which carbon atom is negatively charged here? Like, is it gonna be this one, this one, this one, this one, or this one here? Which one is gonna be the negatively charged carbon?
The one attached to the magnesium.
Yeah. The one directly attached to the magnesium bromide is the negative charge. So I'm going to star that right there to represent my nucleophile, right? So now what we say here is that this carbon here is going to attack this CO2, right? Not the other way around. The CO2 does not attack the magnesium like that. So do not draw the arrow like that, right? Okay, so we're going to draw that attack like that. What else has to happen after that attack? Because we're trying to make a new bond here, but we're going to break the octet rule if we don't do anything else.
Then one of the double bonds breaks and you put a charge on the oxygen.
Yes, a negative charge, right? So as a result, MGBR goes away. The starred carbon that we had attacked the dot carbon, right? This right here is the new bond between the star and dot carbon from the attack. The dot carbon here still has a carbon double bond oxygen, one of it. So I'm going to draw that out like this. And then the other carbon double bond oxygen, we pop that double bond onto the oxygen, giving that oxygen a negative charge, right? But now this is a single bond like that. Okay, nice. And then what would be the next step here?
The negative charge on the oxygen would go to the hydrogen.
Yep, it would get protonated by the acid that we have from the acid workup, H plus workup. leading to a neutral carboxylic acid like this. Right.
So it
And
always adds a carboxylic.
acid, yes. This route here, when you see haloalkane react with Mg creating the green neutral agent reacting with CO2 and acid workup, it would always create a carboxylic acid.
Okay.
Right? And then this is the neocarbon here from the molecule, which comes from the carbon dioxide from the CO2, right there, like that. Okay, which is that carbon right here. Okay. Okay. So now let's move on to the next one, which is this one. Okay. So are you familiar with carboxylic acid derivatives?
Oh, but not too much.
So let's go over that. Carboxylic acid is going to be a carbonyl, right? So a carbonyl is a carbon double bond oxygen attached to a hydroxy group, OH group. So this right here is the carboxylic acid. Let's say this right here is the leaving group. That leaving group could be substituted with anything, right? It could be substituted with a halogen X, where X mostly can be like chlorine or bromine. That's acyl halide, right? It can be substituted with another carboxyl group. Could be substituted with an OR group, or it could be substituted with an amine group, right? It could be like that, it could be like that, or it could be like this, right? There's names for these right here. The similarity is that all of these has a carbonyl, a carbon double bonded to an oxygen. The differences between all of these is the LG, the leaving group, which are these green circles right here. Those are the differences right there. And based on these differences, based on what the LG is, the leaving group is, that's going to give a different functional group. Right, so the first one is going to be named acyl halide. The second one is going to be named an ester. The third one is going to... Wait, no, that's not ester. This is the ester right here. The second one is an anhydride. And then this one is going to be an amide. But there's like different types of amides, right? Because of the different amines here. This is the parent functional group, carboxylic acid. And I'm actually going to put that carboxylic acid in between the anhydride and ester here, right? And each one of these carboxylic acid derivatives will have different properties, right? Different reactivity. So in this specific order that I gave you right here, the reactivity will increase from right to left, right? Meaning that the acyl halide is the most reactive derivative out of all of these derivatives, right? The amide is going to be the least reactive derivative. A cousin of these derivatives is going to actually be the nitrile, which is a carbon triple bonded to a nitrogen right there, right? That's a cousin of the carboxylic acid derivative, right? Now, there's two major reasons why acyl halide is the most reactive and amide is the least reactive. The most important reason here, I would say, is leaving group ability, right? So if you were to imagine all of these groups leaving with a negative charge, like let's say X minus, this one is carboxylate, this one is OR minus, this one is OH minus, this one is NH2 minus, right? This X minus here is the best leaving group because it's the most stable with the negative charge. It's the most electronegative atom because it's a halogen, like chlorine or bromine, so it can hold that negative charge the best, right? This carboxylate here is the second best because the similarities between all of these three here is that there's a negative charge on oxygen. So electronegativity does not matter here because it's the same atom, oxygen, right? But we see that this negative charge here on this leaving group can do resonance with the carbonyl. And when a molecule can do resonance, it's going to be more stable. So that's why this leaving group is better than these two leaving groups right here. Right? Okay. And then these two leaving groups are going to be very similar. So that's why I put carboxylic acid on top of ester, because they're going to have similar reactivities. Right? Now, the worst leaving group here out of all of this is the NH2 minus, because the negative charge is on the least electronegative atom compared to oxygen and halogen. So the negative charge here is unstable, right? So that's why it's the worst leaving group. That's why it doesn't really want to react, because it doesn't want to get to this bad leaving group here. The other important factor here is carbonyl carbon electrophilicity, positive charge, right? Which is going to be talking about the positive charge or electrophilicity, how positively charged all of these blue carbonyl carbons are, right? If you look at the acyl halide over here, for example, that, since it's the most reactive, it's the biggest positive charge, whereas the amide will have the smallest positive charge, right? So if a nucleophile comes around, it's going to be most attracted to the acyl halide because it has the biggest positive charge, right? And it's least reactive to the amide because it has the smallest positive charge. Now, there's two reasons why this acyl halide has the bigger positive charge. One of it is because it's attached to a very electronegative atom, right? Like chlorine or bromine. And that electronegative atom is going to withdraw electrons from the carbonyl carbon. It's going to steal the carbon's electrons away. And we know electrons are negatively charged. So that's why this carbon here is positively charged, because it's losing negative charge, losing electrons. Okay. The other reason is, if you look at this halogen over here, it has 3 pairs of electrons. It doesn't really want to give it away and do resonance with the carbonyl. It can, but it doesn't really want to, because it's really electronegative, and chlorine and bromine are relatively big atoms. So they can't do resonance well with this carbonyl. And if they cannot do resonance well with the carbonyl, they're not donating electrons to the carbon, meaning that this carbon here is not gaining negative charge like that, right? Okay. Whereas if you look at the amide over here, amide has a pair of electrons, and it's less electronegative than the halogen or oxygen is. So this pair of electrons here is going to actually be willing to donate electrons and do resonance with the carbonyl right there. And because this carbon here is going to gain electrons from the nitrogen, it's gaining negative charge, right? Because electrons are negatively charged. This carbon is gaining negative charge, meaning that its positive charge is getting smaller, like that. Okay, so these ones here are going to be in the middle, in between the acyl halide and amide. Okay, now let's go back to here. Wait, so to answer this right here, I gotta go over a little more concepts, right? The acyl halide and anhydride are the top 2 most reactive carboxylic acid derivatives, right? And that makes sense because we already explained why this is the list of reactivity. And acyl halide and anhydride, we see that they're the top 2, right? Acyl halide is number 1, anhydride is number 2. Okay, because they are the top 2 most reactive derivatives, when we try to react them with a nucleophile, they do not need acidic or basic or heat to do the reaction. They don't need extra energy to do the reaction. They could react in neutral conditions. Like if you put water in any of them, it could react. If you put alcohol in them, it could react. If you could put amine in them, it could react. We don't need acid like H2SO4 to react. We don't need base like NaOH to react, right? Whereas these less reactive derivatives will need acidic conditions or basic conditions or heat to react. Okay. Another important thing to know is that all of these carboxylic acid derivatives can convert back to the parent original functional group. And there's a very specific name of that reaction called hydrolysis. Right? So when you hear the word hydrolysis, that's a reaction that requires water. Right? And the hydride and acyl halide
Quick question.
need water. Yeah.
Isn't the last one like non-reactive in hydrolysis?
The last one here can do hydrolysis, but not with water alone.
Okay.
Right? It would also need acid, H2SO4, and heat with it to do hydrolysis.
Okay.
Right? Because it's the least reactive, it needs an extra push, which is an acid catalyst and heat to do that.
Okay.
Whereas acyl halide and anhydride, they could go to the carboxylic acid with just water, nothing else. They don't need acid or heat because they're the most reactive. Right. Okay. So let's go over here. What two functional groups do you see in this molecule over here? Right. I'll give you a hint. It's gonna be two carboxylic acid derivatives.
Could you repeat the question one more time?
Yeah. So we see this molecule over here. There's gonna be two functional groups present. What two functional groups do you see in this molecule here? Like functional group meaning like ketone, aldehyde, carboxylic acid, acyl halide, anhydride, ester, amide, nitrile, like any of those.
Look at the right and left side. So like the right side has like a what is it called? A halide.
Acyl
Like, has
halide.
an X. So Cl is like a halide. So it's an acyl halide on the right, and then the left side has the double oxygen, the carbonyl, and another oxygen. So that's which one is that? Ester, I think.
Ester, yes, ester.
Got it?
Right. Does that make sense, Zenith?
Yeah.
Yeah. So, like, don't look at it like this. Like, there are like carbonyls here alone, oxygens here alone, and chlorines here alone, but there's certain specific way that they're arranged together is going to be organized and characterized by a certain group, right? Like the way that I circled this group here, that's the acyl halide. The way that I circled that group there, that's an ester, right? To be more generic, an ester is going to be a carbonyl, which is a carbon double bond oxygen, attached to an OR group. Whenever you see R, that's a hydrocarbon chain, like carbons and hydrogens, right? And we see that here. This is the carbonyl group, and then this is the OR group. The R group here turns out to be a methyl group, like that, right? And then this carbonyl here is attached to a halogen, and because they're next to each other, that's an acyl halide. Halide for halogen, acyl for carbonyl, like that. Okay. Now, based on that, which one is more reactive, acyl halide or ester? Based on this list that we went over here, which one is more reactive?
Acyl halide.
Acyl halide, and we see that we're reacting it with water. And what do you think that acyl halide would turn into if we react it with water? Just water, no acid or base, right? That's gonna, like, when you see water, what is that reaction name that we think of? Hydrolysis, right? Hydrolysis, which will always convert it back into the parent functional group, carboxylic acid, right? So because we're not given acidic conditions here, only the acyl halide is able to react with this water in neutral conditions. this ester here would not turn into the carboxylic acid because the ester is one of the less reactive derivatives. So that ester is gonna not react. It's unreactive because there's no acid there, right? So the ester stays as is because there's no reaction there. And then the acyl halide will become a carboxylic acid like that. Okay. Let me give you a similar one to practice with. So let's say we have something like this. And we react this with water. How would you approach this problem here?
Would it attack the amide?
So this is, are we given so in the reagents, right? Let's think about the conditions. Are we in acidic conditions, basic conditions, or neutral conditions?
Sure.
Yeah, so when you think of acid, right, what do you think of? Like, what reagent do you think of when you think of acid? Like, what specific thing do you think of when you think of an acid?
Like, which type of reagent?
Yeah, like any reagent that you are used to seeing when you think of acid.
Like HCl.
Yeah,
or-
HCl.
Yeah.
Or do you know any other ones? Like let's think of, let's say, one more. HCl or
H2SO4.
yeah, H2SO4. And you notice how both of those acidic conditions has H on it? That H right there is going to be the proton. So whenever you see H, that's most likely going to be acidic conditions like H2SO4, HCl, HBr, H3PO4. A lot of these with H's are going to be acidic conditions. Right. In basic conditions, think of negative charge for basic conditions. So like when you see NaOH, Na, whenever you see that, it's always positively charged. Right. So if that's positively charged, the thing that it's going to be attached to is negatively charged. Right. And then Na is a spectator ion. It's not really going to do anything, so we ignore that. The thing that's actually going to do something in the reaction is the OH minus hydroxide ion. And because we see that, that's the base right there. Basic conditions. It doesn't have to be that. It could be NaOR, like that, whatever the R group is, meaning that the base here is this ethoxide here, right? If you see like neutral molecules like H2O or alcohol like ROH, like ethanol, like that, that's neutral conditions. We're not in acidic conditions. We're not in basic conditions. It's neutral. It's in between, right? And so if we're in neutral conditions here, we're gonna, so the only things that could react with the neutral conditions here is the top two most reactive derivatives, right? And we see here, what were the top two most reactive derivatives?
The acyl halide and the anhydride.
Yes, acyl halide and anhydride. Do you see any acyl halide or anhydride here?
Is it the bromine?
Yeah, this one right here.
Yeah.
Right, the carbonyl with the bromine is the acyl halide, which will react with this neutral conditions water to turn into carboxylic acid, the parent functional group, through hydrolysis. Right, this right here is an amide. Right, so let me label that to make it more clear. This right here is the acyl halide functional group. This right here is the amide, like you mentioned earlier, right? And if we look at the reactivity list, amide is one of the least reactive derivatives that needs acid, base, or heat to react, right? But because we're given just water, no acid, no heat, like no H2SO4, no HCl, no base, like no NaOH, we're only going to react with the acyl halide, converting that acyl halide into the carboxylic acid like this. The amide, because it doesn't react, it's gonna stay the same like that. Okay. Any questions on that, Zenith?
So anytime it's reacting with H2O, it just becomes a carboxylic
Acid.
acid. Yeah.
Not all the derivatives, the top two most
Okay.
reactive derivatives, the acyl halide or the anhydride, right? So if you see something like this, and you react that with H2O, that's going to so we have two things here. We could like say that, let's say this is the leaving group. That means that we're gonna get OH like that, where OH is the new leaving group, and then the leaving group that left is gonna be this right here. So let me actually code that differently. That's that leaving group right here. So this green circle thing is this green circle thing right there. This pink OH here comes from the water like that, and then this purple carbonyl is that purple carbonyl right there. So what we're basically doing is substituting the leaving group with the nucleophile water here, right? So this purple group here was attached to the green group, but now the purple group is attached to the pink group, right? And the green group got kicked out as a leaving group, like that. Okay. Same thing as for here. Like what we basically did here was we substituted the bromine with the OH, right? The OH came from the water, the H2O, right? The bromine, where did it go? It went away as a leaving group, Br minus, like that. Okay, but we don't have to write that as a product. Okay. Let's move on to the next one. Okay, let's look at this one over here. Okay, this one here is going to be very similar to this last synthesis problem over here. So let me teach you this reaction first before we go over that problem. So I'm gonna teach you acetal formation in acidic conditions, right? And hydrolysis of it, going backward because it's reversible. Hydrolysis. Okay. So let's say we have a carbonyl. Let's start off simple. Let's start with this ketone here. A carbonyl is a carbon double bond oxygen. If we react that with an alcohol, right? Let's start off with something simple, which is this ethanol over here. In acidic conditions, H2SO4. Here's how you're going to predict the product quickly. Find the carbonyl carbon, which is this pink carbon here that I color coded. The carbon double bond oxygen is not going to be there anymore in the product. It's going to go away. Right, so let me draw out that backbone and that pink carbon right there. The carbonyl is not there anymore. This is going to be in excess, so there's going to be a lot of those alcohols around. In acidic conditions, we're going to add 2 of the OR groups of the alcohol. So the hydrogens are not going to be there. Right, I'm going to go over the mechanism as well, but I'm going to show you the shortcut, the trick on how to predict the product quickly if this shows up for predict the product. Right, so we're going to add this 2 times to the pink carbon, which was the carbonyl carbon, like this. 1 time right here, another time right here. So to make it more clear, this highlighted green part right here of the alcohol, OR, is going to be this OR group right there, 2 times, right? These are the new bonds formed, like that. Okay. Any questions on how I got from here to here, Zenith? Okay, that's good. So let me show you how we do that mechanistically, like step by step, arrow by arrow. So this carbonyl carbon here, what charge would you say that has? Partial negative or partial positive charge?
Partial positive.
Partial positive. And if it's partial positive, would that be the nucleophile or electrophile?
Electrophile.
Electrophile, right. This right here, do you see any atom that has a pair of electrons?
The oxygen.
Yeah, the oxygen, but they weren't given to you, but there's two invisible pairs of electrons like that. And if you see electrons like that, what charge would this oxygen have right here? Partial negative or partial positive?
Partial positive.
So let's think about oxygen, which is attached to this carbon and hydrogen over here. What's more electronegative, oxygen or carbon? What's more?
Oh,
Huh? Oxygen. Right. And if
yeah,
oxygen is more electronegative, what charge would that oxygen have?
a negative charge.
Yeah, negative charge. And if that's the negative charge right there, would that be the nucleophile or electrophile?
Nucleophile.
Nucleophile, right. So what would attack what?
The nucleophile would attack the electrophile. Correct?
Yeah. The nucleophile would want to attack the electrophile like that, not the other way around. We don't want the electrophile to attack the electrophile. Like that can't happen, right? Because what attacking means is like we're trying to make a new bond, right? And what does one bond represent? How many electrons are in one bond between, let's say, two carbon atoms? How many electrons are in a bond?
2.
2 electrons. Where do those 2 electrons come from? From the pair of electrons like that, right? Which can attack this carbon to make that new bond right there, right? Okay. But right now, this is a weak electrophile. This is a weak nucleophile because they're neutral, right? There's no like full positive or full negative charge. They're weak. So if the acid was not there, right? This right here would be no reaction. NR, no reaction, right? Because this is a weak electrophile, weak nucleophile. But because we have the acid here, this right here is the acid catalyst, catalyzing the reaction to occur, to make happen, right? So in acid here, what do you think is gonna get protonated in this molecule? What atom?
The oxygen.
Yeah. And I'm gonna draw out the mechanism like this. The oxygen here has 2 pairs of electrons. That oxygen is gonna use one of its pairs of electrons to grab a hydrogen from the acid that we have. In this case, it's H2SO4, right? When this oxygen here is gonna grab that hydrogen using one of its pairs of electrons, the bond between the hydrogen and whatever is attached to, in this case, like OSO3H, that bond is gonna go on to the oxygen like that, giving us this intermediate here. So the carbonyl oxygen is now bonded to a hydrogen like that. And because this oxygen has 3 bonds, 1, 2, 3, that oxygen would be positively charged, right? Its formal charge would be positive 1. And then the side product that we formed here is the conjugate base HSO4 minus, OSO3H minus, like that, right? Okay. Now, this oxygen here, do you think it's stable or unstable with the positive charge?
Unstable.
Unstable, right? It doesn't want that positive charge at all, so it's very angry right now, right? And because it's very angry, it's gonna want to like pull on the electrons of this carbon even more. And if it's pulling on the electrons of that carbon even more, do you think this carbon here is going to be positively charged or negatively charged if that carbon is losing electrons?
Negatively charged.
So negative charge are going to be like having a lot of electrons, electron rich, right? So because this carbon here is losing electrons from this angry oxygen, it's losing negative charge, becoming more positive charge.
Okay.
Right, because it's losing its electrons, losing its negative charge. So it's gonna become even more positively charged because it's losing electrons more. Right. So now we consider this as a strong electrophile. This is an activated carbonyl now, ready for a nucleophile to attack it. Okay. So now we bring in our alcohol, which is this ethanol over here, and this alcohol here is going to attack the activated strong electrophile, which is this over here. And then what that means is that we're trying to make a new bond between the oxygen and carbon right there. But that's going to break the octet rule. What can we do to conserve the octet rule? What other arrow do we have to do to conserve the octet rule here?
From the double bond to the oxygen.
Yes. Double bond to the oxygen, like that, which would give us this tetrahedral intermediate. So if I color code this carbon here, and let's say I color coded pink, so let's keep it consistent. This is the pink carbon right here. It was double bonded to an oxygen, but now that double bond became a single bond oxygen, like that, right? You know how before this oxygen was positively charged? Now it's neutral, right? The reason why is because it gained a pair of electrons from this bond. this bond here, which has 2 electrons, are gonna go onto the oxygen, giving it a second pair of electrons and making it neutral, like that, right? Now, this is gonna be the new bond that we just formed between this oxygen, which is this oxygen, and this carbon right here. What is attached to this oxygen over here in this molecule? What 2 other things are attached to that oxygen?
The hydrogen and the carbon.
Yeah, the hydrogen and this carbon here, which is going to be attached to this whole group. So the ethyl group right there, which I'm going to draw out like that. Right. Now this oxygen here has 3 bonds and 1 pair of electrons. What should the former charge of this oxygen be?
Positive.
Yeah, positive charge. Right. So this is our tetrahedral intermediate over here. Now, once you have this tetrahedral intermediate, I want you to know these 2 points here for this mechanism. Right. You're going to want to deprotonate the group you want to keep, right? Which will tend to be the neal group. And then you want to protonate the group you want to kick out, which will be the old group. Okay, so this right here is the neal group that we added onto the structure, because that is the alcohol that attacked, right? Which is that one right there. This is the old group, which is the carbonyl. Right? We want to keep this neal group in, and we want to kick out that old group right there. But we see that this neal group here is a good leaving group. Right? Are you familiar with good leaving group and bad leaving group?
Yes.
Yeah. So if this group were to leave, it's gonna be stable, because whenever a group leaves, it leaves with a pair of electrons, or -1 charge, right? So +1, -1 is neutral, so this neutral structure is very stable. This right here is a bad leaving group, because when it leaves, it's gonna leave with a negative charge, which is unstable, very angry. We don't want that. Okay, so that's a problem, because we want this to be the bad group, like bad leaving group, and we want this to be the good leaving group, right? Because we want to keep this, we want to kick this out. Okay, so we could deprotonate this group to make that into a bad leaving group, and the base that we could use to deprotonate that is the conjugate base that we formed in the first step, right here, the HSO4 minus, right, which came from the first step over here. That's gonna come back to grab this hydrogen and a bond between this hydrogen and oxygen here. Those 2 electrons are gonna go onto the oxygen like that. Okay, which will give us this intermediate right here. Okay, OH stays the same. This oxygen here is now neutral because it lost a hydrogen and it gained a pair of electrons from this bond right here. So it's now neutral. That's the bad leaving group. That's good. Now, to make this into the good leaving group, make it positively charged, we can protonate it, right? Proton is a hydrogen. So if we protonate it, we want to add a hydrogen to this oxygen over here, right? We deprotonate this oxygen, meaning that we got rid of a proton. We got rid of a hydrogen, like that, okay? So this oxygen here is going to get protonated by the acid that we just reformed in the previous step to give us this tetrahedral intermediate over here. Okay. Now this is good because we see that this right here is the bad leaving group, and that's good because we want to keep that group. This right here is the good leaving group, and that's also good because we want to kick that out. Okay, now to drive this off, right, we're not just gonna kick it out like automatically like that. You can, but it's gonna like have resonance structures. The best way to draw this mechanism is that the other group, the bad leaving group with a pair of electrons, right, is gonna go down to form a double bond, right, between this carbon and whatever this atom is, right? And we make that double bond right there. This carbon will have 5 bonds, 1, 2, 3, 4, 5, and that's bad. We don't want that. That's gonna break the octet rule. So we gotta kick something out if we try to make this double bond right here. And the thing that we're gonna kick out is the good leaving group that we formed over here, right? So we're gonna draw another arrow, kicking that water out, which is a good leaving group, okay? And that's gonna give us this right here. Okay, and this oxygen has 3 bonds, so it's positively charged, and then water left as a side product, so that's gonna be the water floating around like that. Any questions on how it got to here, Zenith? Okay. Now, once I have this, is this oxygen happy or angry? Is it stable or unstable?
Unstable.
Unstable, right? Because it's positively charged, meaning that this carbonyl here, is it strong electrophile or weak electrophile? Is it like, does it have a big positive charge or a small positive charge?
It has a small positive charge.
So if we think about it, right, like previously, this angry oxygen here, because it's very angry, it's positively charged, it wants to steal the carbon's electrons more, right? It wants to pull the carbon's electrons more. And if this carbon here is losing electrons, it's losing negative charge, meaning that it's gonna have a big positive charge like that, right? Meaning that it will be the electrophile or nucleophile, this carbon here, if it has a big positive charge. So what is positively charged, nucleophile or electrophile?
Electrophile.
Right, electrophile. So this carbon here is gonna be the electrophile, meaning that we're gonna bring in another alcohol because we have a lot of them around in the environment, in the solution, which is gonna be the nucleophile to attack the electrophile like that. Right, meaning that we're trying to make a new bond between this oxygen atom and carbon atom right there. But to do that, we're gonna have to pop that double bond to oxygen to give us this tetrahedral intermediate here. So that's the pink carbon. The double bond oxygen is gonna become single bond oxygen neutral. This is the new bond right here between this oxygen atom and carbon. And because this oxygen has 3 bonds, it's positively charged. Now there's one last step here to go from here to here. This proton we don't want, so we gotta deprotonate it, right? And what we could use to deprotonate it is use the conjugate base that we formed earlier, which is HSO4 minus. I'm gonna draw it out like that, which is gonna grab the proton. The bond between the proton and oxygen being grabbed is gonna go to the oxygen to give us this final answer over here. Okay.
Can you explain the middle step one more time?
The middle step, this one
Yeah.
right
So you have that one part where it's, so let me see, hold on.
Mhm.
So you have HSO4 minus, right? And then that acts the H2O.
From this point or from this point over here?
The one on the bottom right. Yeah, why do you form a double bond? I don't get that.
Okay, yeah. So we are gonna form a double bond to drive this good leaving group off because we don't want this group anymore. So to drive it off, we're gonna form a double bond to kick that group off right there. Right.
Is it always the same? Like you're always forming double bond to kick off
leaving group.
H2O. It's not like a HSO4 minus thing.
No, it's not a HSO4 minus thing. That's a proton transfer step. Like anything with HSO4 minus or H2SO4, that's proton transfer. This is not a proton transfer step right here, right? This is what we call collapsing.
Yeah.
The tetrahedral intermediate.
Okay.
Right. So this doesn't include H2SO4 or HSO4 minus. Right.
I think I'm actually confused a little bit about the step immediately after that. How do you get another oxygen to be able to create the new?
Yeah. Right. Like how do we get another oxygen from the alcohol over here?
Yeah.
Yeah. So you notice how we used one already from here. So this is like the first equivalent. So the first mole you could think of like that. This right here is gonna be the second equivalent, second mole. And that's because this right here is an excess amount. There's more than one of that around in the solution.
Okay.
Right. Okay.
How do you know? Yeah, that's the thing too, is like, how do you know if it's like in excess, I guess?
Yeah. So if the professor doesn't put 1 EQ or 2 EQ and they just put like the reagent, assume that it's an excess.
Got
Okay, cool.
Yeah. Okay. Any questions on any of these steps over here? Okay, so
finish up the last part of it. So you have the oxygen forms a double bond, and then you kick off the H2O, and then what happens after that? You add another
this step over here.
OH double. Okay.
Oh, so this right here is a proton transfer step because we're using HSO4 minus as a base to get rid of this hydrogen over here on this oxygen, right?
Okay, so you have SO4 HSO4 minus. That's where the HSO4 minus comes in again then, basically.
Yeah, whenever you want to get rid of a proton, get rid of a hydrogen, that's when you bring in HSO4 minus. HSO4 minus will always do an acid-base reaction and take away a proton, take away a hydrogen from something.
Okay, got it. So then you have a carbonyl from that double bond formation, and then you have a positive on that, and then your OH minus, the electrons attack the carbonyl, and then the double bond attacks the positive, so that's neutralized.
Yeah, this is neutralized because when this nucleophile attacks the carbonyl, one of the bonds of the double bond will go on to the oxygen.
Negative, positive. Okay, then you have
neutral. Yeah.
Oxygen, and then let me see, hydrogen bond. Okay. And then the oxygen attacks. And then the H, when that other OH adds on, that forms a positive, and then the HSO4 minus balances out.
Right.
Hydrogen and then oxygen.
Yes.
Okay. Got it. Wonderful. Thank you.
Yeah. Of course. This right here is going forward from a carbonyl, which is a carbon number 1 oxygen, to an acetal. An acetal is a carbon that is bonded to 2 OR groups, right? And I could highlight that in pink right here. This carbon that's attached to 2 OR groups, which is this pink carbon right here. This is an acetal because this carbon here is attached to 2 OR groups. An R group is whatever hydrocarbon chain, right? OR, OR, like that, making this overall an acetal, like that. Okay. We could go backward. We can convert an acetal back into the carbonyl through hydrolysis. So when you hear the word hydrolysis, what reagent do you think is going to be involved here?
Water.
Water. Yeah. So water is going to be involved here. So let's go backward. Let's have the acetal that we created from the beginning, and we react it with water because we're trying to do hydrolysis here in acidic conditions, and we're trying to get to this carbonyl over here. Now, I'm going to ask you guys, what do you guys think is going to happen in the first step of the mechanism here? Right. I'll give you another concept to understand. Acid-base reactions in organic chemistry are one of the fastest reactions you have in OChem, right? So when you see an acid somewhere, try to look for an acid-base reaction first, right? So we have an acid here. What do you think this acid is going to do to this molecule over here?
Protonate one of the oxygen.
Yeah, protonate one of the oxygen. Give oxygen one of the protons. So I'm going to draw it out like this. Protonate one of the oxygens. And let's see what we just created. We just created this over here, where what charge would this oxygen have here that just got protonated?
Positive charge.
Now, overall, is this structure a good or bad leaving group?
Bad leaving group.
So if this group leaves right here, what's +1 -1?
Oh, yeah. Be neutral, so it's a good leaving group.
Yeah, good leaving group. It's gonna be stable, right? How about this one here? How about this leaving group?
It's a bad leaving group because they'll have a negative, right?
Yeah, negative charge, which is very angry, very unstable. So bad leaving group. This right here is a good leaving group, and that's a good thing, right? Because we see in the product we don't want any of that at all, right? So what can we do to drive this good leaving group off?
form a double bond
on the other side,
on the
which
other
is
side.
gonna be like that. Okay, let me draw it this way. That double bond, and I kick off that leaving group to give me this, and I'm gonna draw out the leaving group on the side like that. Wait, which is this thing right here, that left. Okay. Now, what charge would this oxygen have over here?
A positive charge.
Uh-huh. Positive charge. And now, look at the carbon attached to it. Is it gonna be a nucleophile or electrophile?
It's gonna be an electrophile.
Uh-huh. Yep. It's gonna be a very strong electrophile because this positive charge oxygen is very angry. So it's gonna like pull on the carbon's electrons even more, stealing its electrons, stealing its negative charge, making more positive charge. So what nucleophile would attack that electrophile from the reagent?
The H2SO4.
Oh, so H2SO4 is the acid, right? Which would not be the nucleophile. It's gonna be the H2O instead. H2O water. So how would you draw the arrow here? Like where would you start the arrow and end the arrow? For the water to the nucleophile water to attack the electrophile carbonyl carbon.
From the carbon to the hydrogen? Or yeah, right? From like more charged one.
So this is the electrophile right here. What atom of this water molecule is the nucleophile?
Oh, the oxygen.
The oxygen, right. So the partial negative oxygen is going to attack this partial positive carbon like that, right? What other arrow would we have to draw here?
From the double bond to the oxygen.
Yeah, like that. And that's going to give us a tetrahedral intermediate like this. What would the overall charge of this oxygen be as a result of this step? Like if it gains a pair of electrons.
It'll have no charge. It'll be neutral.
Yep, no charge, neutral like that. There's oxygen here, which is attached to two hydrogens, 3 bonds, positive charge, giving us this tetrahedral intermediate. Okay, so we have this group and this group. Which group do you want to keep? Which group do you want to kick out?
You want to kick out the H2O and then keep the other one.
So the H2O here is the better leaving group, and this is the bad leaving group, right? But H2O is actually the one that we want to keep because that's going to lead us to the final product here, which is the ketone. If we were to go back down and kick out that leaving group, which we can do, right? We're going to go backward to here. We're going to go back to what we started with, right? But if we want to get to the carbonyl, we want to keep this H2O and kick out that right there. So we're going to reverse the roles here. We're going to make this into a bad leaving group somehow, and we're going to make this into a good leaving group somehow. How can we make this into a bad leaving group? How can we neutralize this right here? What can we use?
Deprotonate it?
Yeah, deprotonate it using the HSO4 minus. Oh, this is hydrogen like that. Okay, that's good. Now this is a bad leaving group because it lost a proton. It's now neutral, so that's good. We can keep that. How can we make this into a good leaving group?
Protonating it.
Protonating it using the H2SO4 that we just formed in the previous step. Grab the proton there, give us this intermediate.
So we use the acid to protonate or deprotonate it, and then you use the H2O to attack the carbon, right?
Yes, we use the H2O to attack the electrophilic carbon.
Okay.
From make sure the carbonyl carbon is is activated by this positively charged oxygen right there, like that. Yes. Okay. Okay. Now once we have that good leaving group in place, what can we do to drive that off?
Create another double bond.
From the other side, like this. Kick that out. We get this. This oxygen is right there, positive charge. The side product is this leaving group that left. Now, what can we do to get to the final answer here?
protonated again?
Yep. Get rid of that proton with the HSO4 minus. Boom, boom. And then we reform our acid catalyst and get our final desired product there, like that. Okay. Any questions on that, Zenith?
No, I definitely understand it a lot more.
That's good. That's good. It's like a story, you know, behind the arrows. Like, do you protonate the group you want to keep, protonate the group you want to kick out? Like instead of just memorizing and looking at the arrows, just doing it, it's better to understand why they're going there. Like, what's the nucleophile? What's the electrophile? What group wants to leave? What group wants to stay? Understanding that will make everything like click more easily, right? Yeah, and also color coding it, like where groups are coming from as well, helps a lot as well, right? Okay, but good luck on your midterm this Friday. Definitely tell me how it goes, and we could definitely prepare and review for your like previous midterms on office hours, future office hours, Saturdays to Sundays, and then yep. I wish you the best of luck, Zenith, and
I actually have one quick question about the notes that you took while we were on here. Is there any way that you could share a copy of this with me at all?
Yeah, I can send it to your email.
Okay.
These notes, and Trinity as well, and I'll send you the recording of the session as well for you guys to review.
Okay, thank you.
Of course. Yeah.
Have a good night. Thank you.
You too. Good night.
Thank you. Katya says hi, by the way.
Oh, Katya? Oh, Katya's there right now?
Hi.
Hey, Katya. Oh my gosh, it's been a while.
I know. Thank goodness I don't have to do that anymore. I try to help them the best I can, though. Sometimes I'm right.
Oh yeah? You still remember some of the stuff, right? Like maybe some nomenclature?
Yeah. No, I help her with the reactions.
Yeah, she's pretty smart, low-key. She does kind of help me with a lot of stuff. So yeah, you did good.
That's great. That's great.
Yeah, real.
Yeah.
Oh man.
I repeat the words over and over again. It's stuck in the brain now.
Yeah, it's terrible. Oh.
Yeah. Okay. Good night, guys.
Good night.
Bye-bye.
Bye. Thank you.